close.
No, no.
It looks
Who are
like
you rooting for?
Trump, bro. Trump's gonna get it. I'm telling you.
I don't really care, but it's just interesting because, like, well, you know, the amount of entertainment that comes out of it is ridiculous.
Oh, all the memes of those angry liberals.
Yeah.
I'm just gonna grab the paper. I'll be back in a sec.
No problem.
All right, I'm back. Oh, by the way, I've got a bunch of worksheets for circular motion questions and all that.
No problem.
Do you want me to send them to you so you have extra questions or?
Yes, please. I would appreciate that.
Yeah, no worries. I'll send them over at the end of the lesson.
No problem.
I'll make a start.
Yeah, so give yourself 25 minutes for this one because you've done well in the past 2 ones.
Yeah, let's just grab a pen. Sick. And a paper. "25 minutes," you said?
Yeah.
Okay.
You can begin whenever you want.
Yeah, I'm just going to set up the timer. There you go. Question 1.
Good luck.
Thank you.
I'm doing it as well, but I'll mute myself.
Yeah, okay. Oh, by the way, I forgot to tell you, in class today we did those banked questions and the conical pendulum stuff. The second time we went through it in class made a lot more sense to me than just the first time. You know what I mean?
Yeah.
But if it wasn't for the first time, I would have had no clue what was going on. You know what I mean? Now I
Yeah.
can come. You know what I mean?
Yeah. That's good.
Yeah.
What question are you up to?
2B. For some reason, I stuffed up for question 1. I was doing something ridiculous, and I figured out it was so simple.
Rolls off.
Yeah, I don't know what I was thinking, but it's all good. I figured it out. What did you get for 2A? I'm an idiot, bro. So do you hear all that cutting and noises and all that stuff outside?
Yeah, it doesn't really bother me though.
It doesn't bother you? Oh, okay, because we're building some stuff outside. If you bothers during the class, just let me know. Just put myself on mute.
No problem. It's all good. Man.
Okay.
How much time's remaining?
For me, I have 9 minutes. Question 3C looks dodgy, bro. And that's it for me.
What question did you get up to?
Well, I did 3D somehow, and then I got up to E, and I looked at the time. I had like a minute left. I'm like, that's it. But yeah.
How'd you feel about that one?
Oh, question 3C was a hard one. I couldn't really answer it.
Yeah.
D, because I didn't have the second velocity, I kind of had to sub in something else. I'm going to definitely lose marks for that. And then E, I didn't answer as well. I ran out of time.
All right.
Yeah.
I finished, but I was just checking on my answers. I can send you the solutions if you want.
Yeah, it wouldn't be bad. Can I read that just before I send it just real quick so I can just go tick, cross, tick, cross?
Yeah, no problem.
Question 1, 0.43 seconds.
Yep.
Yeah. Question 2A, 16.76 meters. Nah.
3.65 meters.
How much?
3.65.
Yeah, that's what I was going to ask you. You're supposed to sub it into that formula, yeah?
Yeah.
Yeah, guess what I did? I, for some reason, thought it was thrown off the cliff on the top.
Right.
Yeah, and I lost marks because of that. And then for B, did you get 31.18?
31.27, but because of the rounding, I'll let it slide.
Yeah, okay. Sweet. And then question 3A, max height 20.41.
Yep.
Yeah. B, 2.04 seconds.
Yep.
Yeah. C, I don't have. For C, you know what I tried doing? Because you don't have UI for the other object, I tried making it from the first formula, the Vy equals Ui plus Ayt. I tried making T the subject and tried subbing into the other equations. It didn't really work out for me.
Fair enough.
Yeah. And then D, yeah, I got kinetic energy was lost because of the explosion by 600 joules difference.
Okay.
Yeah. So the first thing I did was calculate the total energy in the system. The first one I got 1,600.
I got 1,200.
Is the formula half mv squared?
Yeah.
What do I do? Half times 2 times 40 squared. I got 1,600.
Times cos 30 squared.
30. Oops.
Because remember, at the max height, there's no y velocity.
Yeah.
So the only velocity is the x velocity, but Vx equals Ux.
Yep. I see my mistake. Oops.
Okay.
This happens when I don't revise, man. Yeah, I got to start.
I'm sending solutions. My question 3 was so messy because I made a mistake and it cost me a couple of minutes.
Yeah.
But the final answer was basically 70 meters per second at 8 degrees above the horizontal. But you'll see that. I'm sending them across.
Oh, sweet. But yeah,
So,
the way
you go.
sorry, yeah.
No,
Okay. I was about to say the way I would have thought to do question 3 is calculate the mechanical energy for the first start, and then when it explodes, you calculate the mechanical energy afterwards. That's what I had done, but I put in the wrong numbers.
Okay.
Yeah. I'll check the solution. Yeah, see what's happening.
So do you want me to walk you through the solutions?
I'll find the ones I did wrong. 1 was good. Question 2, that was straightforward. I just stuffed up there.
Yeah.
Question 3, A was good. 3, and then A, B was good. Where's C? And A, C. Okay. And max height, the only velocity is Ux equals U cos theta. Yep. By the law of conservation of momentum. Oh, we're supposed to use momentum. I wouldn't have even thought of that. Yeah, could you go through C with me?
Yeah. So for C, all I did was use the conservation of momentum. So we know that the momentum before the explosion has to be equal to the momentum after the explosion.
Yep.
But the momentum before the explosion is going to be mvx. because it's in the x direction.
Mm-hmm.
But Vx equals Ux, so that's going to be mu cos theta. And then obviously, because it's broken up into two separate parts, it's the mv's on both of them is going to be half of the m and then multiplied by the velocity component.
Yeah.
So for VA, we were told that it went straight down. So that's why I had -10, and that's meant to be like a subscript y.
Mm-hmm.
And then all I did was make VB the subject. And then I did the Pythag triangle, got it out, got the angle.
Yeah, I see it. I see it. And that's worth 4 marks.
Yeah.
Wow.
And then just 2 seconds. The other guy I was telling you about for today, he came in just now.
Okay, all good.
Yeah. And then for the last question, do those two projectiles make sense?
For the last 2 questions, D makes sense. Yes. E. Let's see. E. First projectile is from B. The second projectile has the following property. Andrew sub. Yeah, E is all right.
Yeah. So the first projectile, obviously, because after it explodes, it goes straight down. That means it's just going to land where the max height was.
Yeah.
And then for the second projectile, well, that forms a type 3 projectile, doesn't it?
Yeah.
And then you just have to go from there.
Mm-hmm. Yeah.
So how do you feel?
Oh, I feel pretty confident now once I have your solutions.
Yeah.
But yeah.
Can you send me your solutions soon, and I'll just kind of begin the lesson.
Yeah, that's fine. I'll send it to you.
No problem. Hey, Stefan. Yeah. So unfortunately you're a little bit late, so we're kind of tag teaming today. So are you okay with horizontal circular motion?
Yeah.
Like No, like just FC, MV squared on R, and all those things.
No, I don't know yet.
Okay. So we're going to do okay, so we'll start from the beginning a little bit. So Radovan, when you come back, can you tell me what you're up to so I can just kind of tell you what to do?
Yeah, no worries.
No problem. This isn't ideal, but okay. So Stefan, 4 objects can move in circles, just like they've been moving linearly. This is probably what you've looked at in class. And the idea is, if something is in uniform circular motion, well, the word uniform in physics means constant.
Yeah.
So that means that we're going to have a constant speed. What about my velocity?
Velocity will be constant.
No.
No.
Velocity has a direction component.
Oh, yeah.
But if I'm traveling around the circle, my velocity is continually changing.
Yeah.
And the velocity is tangential to the circle, as you can probably see in that diagram.
Yeah.
Now, what happens is, well, we can calculate the tangential velocity in the same way that we can calculate regular velocity.
Mm.
Regular velocity is given as distance on time. So tangential velocity is going to be the total arc length divided by the time it takes to do that arc length. So that's where you have 2 pi r on t,
Yeah.
where t is the period.
Yeah.
Any questions? Okay. So if we go to the next page, we have angular velocity. So just like how we have the tangential velocity, we can also have the angular velocity. So if the tangential velocity is how quickly I'm moving in terms of the arc length, the angular velocity is going to be how quickly the angle is changing.
Yeah.
And naturally, that's just going to be equal to the change in the angle over the change in time. So what happens if you want to convert between the angular velocity and the tangential velocity? Well, let's think about this quickly. Tangential velocity is given as 2 pi r on t. So this is distance on time. The angular velocity, denoted by omega, is a w. Well, that is if it travels a whole circle in a period.
Yeah.
How many radians, because we use radians now, are in a circle?
2 pi.
Divided by 2. That's your angular velocity.
Yeah.
So from there comes this unique equation where V is equal to omega r. So if you ever want to find the tangential velocity, all you have to do is, well, W equals V on R, so on and so forth. So I'm sorry to rush through the theory a little bit, but we can always come back to it if you get stuck. But do you mind just, I think the next page is self-explanatory. Do you mind reading the next page, page 3?
Yeah, I've done a bit of that too in class.
Alright, no problem. If you're confident with it, I'd like you to attempt the concept check on the next page. Alright. Hey, Rad.
Yeah, mate.
What are you currently up to? Have you done all the bank tracks and all that stuff? I think we'll start in vertical circular motion.
Last thing we did in class was that conical pendulum.
Okay, so do you want to start from the conical pendulum?
I was thinking just going straight to energy and work if you want.
Alright, no problem. But are you confident in like calculating bank tracks with friction, without friction, and things like that?
I mean, just get my homework and stuff. Once I go through all those questions, I'll be 100%, but I feel pretty confident.
Okay, that's good.
Because I just want to go through the theory now real quick and then just consolidate it in class. You know what I mean?
Alright.
The second time I go over it.
No problem. So, do you want me to write it on my little whiteboard here that we always use?
Yeah, sure thing.
So, for a conical pendulum, there's a number of forces that are acting at play. So, this is my ceiling, this is my ball, and then it's going to deflect by an angle. And the key word is that that angle is always to the horizontal.
Yep.
If you get told the angle to the vertical. If you ever get told that the angle is to the horizontal, it's referring to this angle here, and you don't really want that. So you just do 90 minus that to get this angle.
Yeah.
Okay. So the idea is, if in a conical pendulum, we have multiple forces, but the main one is the tension force that is acting up the string.
Yeah.
Yep. All right. Cool. But we don't like forces that act at angles. We typically like to do things in terms of x's and in terms of y's. So can you tell me what forces are acting on the ball at this moment in time?
What forces acting on the ball? You've got obviously the tension force. You've got and gravity.
Yeah.
Yeah.
So we have gravity, and then we also are going to have the centripetal force.
Yeah. Is that just the horizontal component of the tension?
Yes, that is.
Yeah.
So that's what I was getting into. So these forces, mg and fc, they're never going to exist by themselves, because think about it. If mg existed by itself, then that means that mg is the net force, so the object would accelerate downwards. But however, we know from experience that this doesn't happen. The ball stays in its nice circle.
Yeah.
So there has to be a force that counteracts this, and this is going to be t cos theta.
Yeah.
And, well, t sine theta respectively. So that allows us to do t cos theta equals mg, and t sine equals mv squared on r. And if you solve through t, you end up getting v equals root gr tan theta.
Yeah.
And it's important to note that that v is basically the tangential speed. So this v is still equal to 2 pi r on t, for example, where t is the period, not the friction, not the tension.
Yeah. So is that the one on F thing? Period.
Yeah.
Yeah. Right.
So that can also equal 2 pi r f, because f is 1 on the period and things like that.
All right.
How is that explanation?
Well, it's pretty solid. And the angle for t cos theta is just the one with the vertical, yeah?
Yeah, this one here.
Alternate angles, yeah. Sweet.
Yeah, exactly. Alternate angles, just like how you said.
And also one quick thing in class, I forgot to say, we did a question something to do with speed bumps.
Yeah. So speed bumps are another form of circular motion. Was never actually asked about it in my what do you call it? In my HSC. Like I never actually encountered it, but I encountered it in 4 units. So I can say I know what I'm talking about.
Yeah.
So when a car goes over a speed bump, or like a hill, for example, we can say that it's going in circular motion.
Yeah.
And well, let's label the forces. Mg, normal, and well, Fc, where the centripetal force is going to be the net force.
Mm-hmm.
Does that make sense?
Yeah, it makes sense. But there was one thing that our teacher said. She's like, suppose that n equals 0, and then she gave us some formula. I'm like, what the?
Yeah.
Like,
Yeah,
that makes sense. You can't have that only works if there's no mass. I don't understand.
Well, how you only set n equals 0 when you're trying to find the minimum speed.
Yeah.
So in this case, can you see how Fc? Actually, I should actually write mv squared on r. Mv squared on r is going to equal mg minus n.
Yeah.
Can you see that? All right.
Yeah.
Cool. So how it works, if we want to find the minimum, then you set n equals, well, n is greater than or equal to 0.
To find the minimum.
Find the minimum speed.
Okay.
So what basically happens is you get v is going to equal root gr. And what that tells us is that the minimum speed for an object to successfully go over this hill is going to be root gr.
Yeah.
It doesn't matter if it's it doesn't matter if it's 1,000,000 kilos, so it has a super high normal, or if it is 1 gram, so it has a super low normal. The speed is the minimum speed for an object to get over it.
Oh, okay. Because I got confused. I'm like, how the hell on earth does that make sense? But it's all right. It's all right. And what if it goes over that minimum speed, or it just turn into a projectile?
Well, it just means it doesn't. Yeah, it actually goes off.
Yeah.
Because there's no normal. So yeah.
Yeah. All right. Sweet. It's all right.
How are you going with those questions, Stefan?
Yeah, I'm just coming to 3.
No problem. Just give me a second. Radovan, did you attempt all of the conical pendulum questions in the concept 5.2.3?
And 5.2.3, I don't think I did.
Okay. Do you want to try one of them for me?
5.2.3. Yeah, I'll give it a shot.
No problem. Thank you. Okay. So for question 3, we should probably go over centripetal acceleration and centripetal force.
Yeah.
So when an object is going around a circle, its velocity is going to be tangential to its to the radius. Yeah. So radius. What actually happens is that the acceleration is actually directed towards the center. Do you want me to prove this mathematically?
Makes sense to me. Like when you're turning, you're going towards the centre more than out.
Okay. So your coordinates on the circle.
Yeah.
You do 4 units, so hopefully this makes sense. The coordinates on the circle, I'm just going to denote with r, and that's going to equal, it's going to be x. R cos theta, and this is in the x direction, so I'm just leaving it as I. Well, you use vectors now, so this should be pretty familiar to you.
Yeah.
All right. So the first derivative, x dot, is just going to equal minus r sine theta I was r cos theta j, and then acceleration is going to equal minus r cos theta I minus r x double dot equals minus x.
So what are the J's?
Oh, that's just the y direction. Yeah, so I is x. So that means that the acceleration is equal to minus the displacement. So the displacement is obviously going to be in the same direction as the velocity. Because if I cut the string,
Yeah.
the ball's going to go off in that direction.
Yeah.
So that means that, well, let's think about this differently. That was a weak explanation. So if this is r cos theta, and this is r sine theta, and this is r. Yeah. Well, that means that if x double dot is minus r cos theta minus r sine theta, then whilst displacement acts in this direction, the acceleration is going to be acting in the opposite directions. So we have a net vector back to the center. And that's just how it works. But you know we asked to explain this.
Yeah.
The acceleration towards the center is given as v squared on r, and the force towards the center, so centripetal acceleration, centripetal force, well, that's going to equal m times ac. So it's going to be equal to m v squared on r.
Yeah.
So question 3, I suggest you write down all the variables. So, you know, the shopping list method that I told you about, write down all the variables and then pick a formula that works with all those variables. And you should get it out. How are you going, Radamon?
It's alright. Not too bad.
What question did you pick?
3.
Okay. Yeah, 3 is a long question.
Mm-hmm. Do you have the answers?
I can tell you them.
Okay. Well, 3A, there's the diagram, whatever, and then B is at 1.34.
Yep, because it's the opposite side. You're going to be using sine.
Yeah, so you just use 2 sine 42 equals x. Pretty much. Yep. C, because it's mg equals t cos theta to balance out the vertical in the bottom, you just solve for t, and I got 3.3.
Yep.
Yep. Magnitude of the net force is acting on the board at the time. Yeah, tension. And then t sine theta is 2.21, so that's the horizontal.
Yep.
Yeah. And I just didn't find the angle for that.
What do you mean the angle?
Like, then I have to put the vertical and the horizontal and find the resultant force with the angle.
Oh, yeah, okay. So you're asked to find the centripetal force for part E, is this right?
Part E, yeah.
Yeah. So for part E, you don't know what V is, so you can't actually use the formula. But if you look at your diagram, can't you see that T sine theta is going to equal the centripetal force?
Yeah. No, so I was still talking about question C.
Oh, no, all you wanted to do for question C was T cos theta equals mg and T sine theta equals mv squared on r.
Oh, okay, because I thought once you find the vertical and the horizontal, you're supposed to find the resultant force, no?
Part D asks to find the tension.
Okay, whatever. You found that in part C anyway, that's all right.
Yeah, so you already did part D.
C. Oh, sorry, T sine theta, the horizontal.
Yep.
Yeah. Do you want to move up to energy and work?
FC is going to equal T sine theta.
Yeah. 3.3 times sine. What was the angle? 42. $2.21.
You used
Yep.
acceleration of centripetal force.
Yep.
And I got 4.
Yeah.
And then the force centripetal, I got 3,600.
Yep. But because they're vectors, you must state the direction they travel in. So you should state that they travel towards the center. Do you want to do another conical pendulum question, Brad, or do you want to move on to bank tracks?
I think we already did bank tracks.
Okay, no problem.
Yeah. I don't know.
So you can move on to. I really want you to do this concept check for homework.
The whole thing.
The whole thing, because if you can do all those confidently, then you'll never need to touch this again.
Okay. Well, no worries. I don't have homework.
So are you ready to move on to energy and work?
Yep.
Okay. How much do you remember from not last year, module 2?
Not so much.
Okay. Okay. Is it possible that you can read the next 4 pages?
From what, 37 to 41?
Yeah.
Yeah. I'll do it to read. Just grab a highlighter.
It's for a refresh.
Yeah.
All right, no problem. How are you going with? Is it coming naturally to you?
Somewhat. Still on the first page.
Okay. Not all of it is important. It's just we just kind of have to look at it all over again.
Yeah. Okay.
Because, well, there was a 3 marker on it in the HSC, in my HSC. Oh, actually, the physics HSC is tomorrow. Oh, that's going to be fun marking that again. Anyway, so yeah, there was a 3 marker in the HSC, so I do recommend you brushing up on this.
Yeah. Okay.
But if you're confident with it, we can leave the concept check for homework and just move on to energy and work in circular motion on page 45.
Okay, no worries. I'll just let you know when I'm done.
Wait, what are you doing? You didn't tell me.
I'm just reading through all this stuff. The work and kinetic
Oh, okay, sorry.
part over here. I just need to get that down.
Okay.
So for question 4,
Mhm.
so we look at the angular velocity.
Give me a chance to read it, please. Question 4. Determine the speed, acceleration, and net force. Does it say anything about angular velocity?
Let's look at acceleration would be v, and for the force.
But angular velocity is given as w, omega. When it asks for speed, always assume that it's talking about tangential speed. Only talk about angular velocity when it asks about angular velocity. And the reason why you should always assume v rather than w is because, well, look at the formula for centrifugal force. It has a v instead of a w. It is also equal to by the idea that V equals WR, but the one on your formula sheet and the one you most commonly use is just going to use mv squared R.
So since he's only made a quarter of a turn, do we times that by a quarter?
He makes a quarter of the circle in 2.1 seconds.
Yeah,
So what's going to be his total time?
8.4.
Perfect.
So we'll get for the whole circle, not just square down.
What are you currently up to, Rad?
Up to kinetic energy.
Okay. So do you just want me to kind of give an overview and we can move on, or are you okay to just continue reading?
If you want, I can give a quick overview. Yeah.
Okay. So kinetic energy is given as half mv squared. That kind of popped up today.
Yeah.
But as we know through the work energy theorem, work is equal to a change in energy. So in kinetic energy, the mass can't change, can it?
Yeah, no.
But the velocity can. So therefore, the change in kinetic energy is given as half m delta v squared.
Yeah.
Yeah, we also have potential energy, which the main one that we look at is gravitational potential energy. So, well, we know that potential energy has the potential to do work. So that means that gravitational potential energy is the potential objects can do work by falling.
Yeah. I remember
And that's
for the gravitational, that's all right.
That's good.
Yeah.
And it's given by U, and U equals mgh. And the same thing as the change in kinetic energy, the change in potential energy is going to be given as, well, delta W, where the mass can't change, gravity can't change. So the only thing changing is going to be the height.
The height, yeah. That's the only variable that can change, yeah.
Yeah. And on the next page, page 41, is something new. This wasn't in your original Year 12 notes, Year 11 notes, but it is there for the new kids. Essentially, because like I had a lot of people ask me, a lot of students ask me, well, how does the work energy theorem work? Like, no pun intended, but like, how can the work be equal to a change in kinetic energy, but that can be equal to a change in potential energy? So essentially what I did, I kind of just mathematically proved how they're equivalent.
Yeah, what's this? 2J. Yeah, okay.
Does that make sense?
Yeah. Sorry.
No problem. And then there's also the mechanical energy. So you just have to be aware of the mechanical energy because that's going to pop up later on.
Mechanical energy. That's like the total energy in the system, yeah?
Yes, and that never changes no matter what.
Yeah, okay.
You can do this concept check for homework if you want.
Yeah.
It's literally all Year 11 questions, but I have to make sure you understand it.
Yeah, all right, no worries.
All right, so go to page 45.
Yep.
Okay. So on page 45, we start energy and work in uniform circular motion. So the first thing we're going to get out of the way is, well, in horizontal circular motion, well, it doesn't dip in height. So delta H, so delta U is going to equal 0 because the gravitational potential energy remains constant. And also, well, there's constant speed. So that means that V squared is going to be constant. So that means that the kinetic energy is constant. So that means that, well, everything is constant in horizontal uniform circular motion. So if there's no change in kinetic energy and no change in potential energy, well, then that means that work is basically zero.
Yeah, if it's not changing, yeah.
Yeah, and this is also proved through the formula. So W equals Fs cos theta. Well, let's think about it. The force acts towards the center, and the displacement acts tangential. And there was a theorem in 3 unit, it's not there anymore, that states that, well, you can probably visualize this, but the radius and the tangent are perpendicular to each other.
The radius and the tangent are perpendicular to each other. Okay.
Yeah. So if they're perpendicular to each other, that means the angle between them is 90. Because 90 is 0. So therefore, work done is 0.
That's fair enough. Yeah.
Okay. But in vertical circular motion, so this is where we kind of start vertical circular motion, obviously something is higher and then it goes lower and then it goes higher. So I do have a change in potential energy. And I might not have a change in mechanical energy because remember, it's supposed to be uniform, but that change in potential energy still gives rise to work occurring.
The changing gravitational potential energy. Because it goes
Yeah.
up and down. Yep. Okay.
Yeah. So for this image of the circle, I want you to derive an expression for the net force when the object is at the bottom of the circle as well as the top of the circle.
Okay. So
How do you?
Yeah. I think,
You don't if you want, we can move on.
yeah.
The first one is the hard question. Alright. This is essentially an experiment. My crappy writing made onto a perfect color. So in this experiment, what you're going to do is look at the formula of centrifugal force, and you're going to analyze the relationships between them. But are you aware of proportionality?
Yeah.
So if A is proportional to B, that means that when I plot A and B, I get a straight line. So that means A equals K, where K is the constant of proportionality. Yeah?
Yeah.
Alright, cool. So all I'm going to do is determine the relationships of the variables in the centrifugal force. So Fc is going to equal mv. Well, we can see the relationships there. Fc is proportional to m because v squared on r can be k, which is a constant.
Yeah.
Also, Fc is going to be proportional to v squared, same logic. 1 on r, so Fc is inversely proportional to r. Also, m is proportional to r, v squared is proportional to r, and m is proportional to 1 on v squared. So all we're going to do, and this was my first crack at it, was worth 30%, so I'm familiar with this because actually this is
Similar.
this is the first part of the crack. The second half is vertical.
Yeah.
Okay, so we'll do an overview of it and then we'll come back to it next week.
Yeah.
Okay, so all you're going to do is, well, let's do this. So what you're going to do, you're going to, well, you can probably read the crack for yourself, but we're going to have a mass and a circle, and we're going to spin it around, and we're going to try to keep it at a constant speed, and we're going to see if the mass changes, what radius happens, and then obviously you're going to see that m is proportional to r. So calculate the gradient of this graph for me. Like, just get up here with the text targets. And then remember the formula is mv squared on r. So from the gradient of the graph, tell me how I can get fc. Just right. What did you get for the expressions, Radovan?
So when it's at the bottom, you have the normal force acting up and the centripetal force acting up and mg acting at the bottom. So when things at the bottom of the circle, it's going to be mv squared on r equals n minus mg.
Close, but I was more talking about like tension, like this is just in the circle.
Yeah.
So like replace n with t.
Oh, okay. Oops.
Yeah.
T, okay. And then when it's at the top, it's going to be mv squared on r equals mg plus t, not n.
Perfect. Yep, because they all act downwards.
Yeah, but I got one question, right? Pretend it wasn't tension and
Yep.
it's going in a circle. And the normal force acting down, gravity's acting down, everything's acting down, yeah? How does it not fall down?
I beg your pardon?
Like, how does the object not fall down if all the force is acting downwards?
Well, because wait, at the top.
When it's at the top, yeah. For example, do you know when you go to like whatever Luna Park and there's whatever, I don't know, like a bike going around that hamster wheel sort of thing. Like, if all the force is acting down, the normal force, gravity, and all that, how doesn't it like fall?
Well, because the net force is a centripetal force that acts in a circle, doesn't it?
Yeah.
So that means, well, if the net force is a centripetal force, it's going to curl in the circle.
And that's why it doesn't fall.
Yeah.
Oh, okay.
If it was just a normal gravitational force that was acting downwards, then yeah. But remember, the centripetal force only applies to circles, so the object has to be traveling in a circle.
Yeah, oh, okay, fair enough. Because, yeah, okay.
Yeah. So if we go to the next page, we can see all the different types of forces that can be asked. So the dot points are all just, what do you call it, like summaries. But the only thing I'd like you to glean from this page is the image at the bottom with the table.
The image at the bottom of the table, yeah?
Yeah, so what we can glean from this is the direction of the centripetal force, where the object is at the bottom or the top of the circle. So the general rule of thumb is that the centripetal force is always going to act towards the center. The normal is always going to act towards the center. The tension is always going to act towards the center. And gravity is always going to act straight down.
Mm-hmm.
And the centripetal force is always going to be, what was I going to say? Oh, the centripetal force is always the net force, as you can probably see in the images.
Is always the net force, yeah.
Do you have any questions?
So far, no.
Okay. Let's see how you go in the concept check.
Okay. Question 1.
Yeah. Do 1, 4, and 5. Do 1 and 5, actually.
1 and 5. Okay.
Yeah, do 1, 2, and 5.
1, 2,
yeah.
5. Yeah. Hey, Alessandro.
Yep.
Yeah, can you help me with question 1?
Yeah, no problem. So, well, firstly, in part A, what force are we being asked to calculate?
Part A. There's no part A. There's only one question.
Wait, what?
5.2.5.
Yeah.
Yeah, just one.
Wait, is this the last page of your document?
No, just page 47.
How many pages do you have?
58.
Yeah. So, like, this is what my page is. Is this what your page is?
A roller coaster. No, mine says a construction team is looking at a building.
Okay. Oh, go to question 2 then.
Oh, what's wrong with question 1?
It's actually a bank tracks question. I made a mistake.
Oh, okay, fair enough. Cross that out.
Yeah.
Question 2?
Sorry.
No,
Yes. Yes, please.
Yeah.
So for part A, let's go through this together. So for part A, what force is it asking us to calculate?
No, I got to read the question first.
Okay.
A roller coaster for a lift, radius 4.8 meters. Okay. The roller coaster has a speed of, yep. Mass. Determine the amount of force on the track that must be designed to withstand the top in order to keep it. Okay, so in order to withstand at the top, so I'm going to have to use the equation that I derived for the top of the circle.
Yes.
So mv squared on I equals mg plus n, and I'm looking
Yes.
n and trying to find n.
Yeah. Well, why are we trying to find n?
Because that's the one thing I don't know in the equation.
Well, remember, the normal force is the force that the track gives off.
Yeah, because like that's
Yeah.
I'll just sub all that crap in. And times v squared on r minus n equals 143400.
Yeah, that's right.
Alright, sweet.
Would you get for part B?
Hold on, just help me with my mom for something. Give me that second.
No problem. So with these types of questions, there's two ways that you can do it. You can either try to memorize all the formulas, or you can just draw a diagram and kind of look at it intuitively. I would personally recommend drawing a diagram and looking at it like that. because you're never necessarily going to know if it's the normal force, if it's the tension force, if it's friction force even, so on and so forth. Like even in the example you told me earlier, that's an example of vertical circular motion, isn't it? Because the car goes up and then down. But in that example, gravity was the force acting towards the center.
Sorry, I'm back.
Oh, you went in there. I'm talking to myself. Great. So what I was trying to say is you can either choose to memorize the formulas or draw a diagram and work it out intuitively. Because like you're not going to know if it's tension or if it's the normal force in the exam. Heck, you even gave me the question you told me earlier was when a car was going over a speed bump. Well, isn't that an example of vertical circular motion? Because the car goes up and then down.
Yeah. Oh, yeah. Because yeah, it is. You just don't see the center point. That's going to be under the ground.
Yeah, exactly. But it's an example of vertical circular motion. But that wasn't normal force or gravity. That wasn't the normal force or tension. That was gravity. Gravity was acting down. But the normal force in this case was acting up. So there's so many different cases that I recommend you actually understanding the content and writing an appropriate diagram.
Yeah. Okay. That's probably why you wouldn't memorize the formulas.
Yeah.
Yeah. Right. Sweet. What am I up to? 2B. Okay. Internally, amount of force struck must be able to withstand at the bottom of the loop.
What did you get for part B?
I think I got the same thing as part A.
You shouldn't have.
Shouldn't have?
If you drew a diagram, you would see that gravity acts down this time. And the
Yeah,
normal
yeah,
force
like-
is the centripetal force to go up.
Yeah, that's what I put mg as minus, yeah?
Yeah. So you have mv squared on r
Yeah.
equals n minus mg.
Yeah, that's what I have.
So that means that n is going to equal mv squared on r plus mg.
Plus mg, yeah.
So what'd you get?
Yeah, the same thing as A. I probably typed something in wrong.
You probably did, because I did the same thing as you and I got two different answers.
Yeah, okay, I'll pop it in again.
So for A, you got 143,400.
Yep.
Okay, so you should get another number for B.
Okay, I'm gonna redo it now. Probably type something in wrong.
Oh, also, okay, I think I know where you're making your mistake. Do not put G is minus 9.8
Why?
because you've already said it's going down.
Oh, okay, I see.
So if you put another minus, and all of a sudden it's going up.
Yeah, okay, I see. I see.
Yikes.
Two, 3, 7, 4, 8, 0.
Yep.
Oh, there it is.
Yeah. And for part C, do you remember what I was talking about earlier in terms of the minimum speed?
The minimum speed.
So
the
when n
not to fall down.
n is greater than or equal to 0.
I don't remember exactly, but I'm pretty sure I know why you're talking about it. The thing where it has to go a particular speed so it doesn't fall from the top, yeah?
Yeah.
Yeah, I don't know.
So the way we approach these questions is that we let n be greater than or equal to 0.
Yeah.
So at the top, we know that it's mv squared on r is going to be greater than or equal, it's going to be equal to n plus mg. So therefore, mv squared on r is going to be greater than or equal to mg. And then all you have to do is solve for v. And this v is going to be the min speed of v.
Minimum, okay. Sort that out.
So that's actual theory. You must, every time you see minimum, set n greater than or equal to 0.
Mm-hmm.
Yeah, tell me what you get.
Okay.
You read the conical pendulum?
Yeah.
Yeah, okay. So how conical pendulum works is, well, something hangs from a ceiling. I have a mass that hangs from the ceiling. And these are just trigonometry questions, basically. They're just big triangles. And, well, as you can probably see from the original diagram, there's gravity acting on the ball. And, well, there has to be a centripetal force acting towards the center. But, because this is a string, we are going to have tension, just like how we had in the other example. And what we can do, well, we don't like this tension being at an angle. We like it either being straight up or horizontal.
Yeah.
So what we're going to do is going to resolve this. So by alternate angles, we can see that this angle is going to be theta.
Yeah.
And, well, this is going to be t cos theta. What do you think this one's going to be?
T sine theta.
Perfect. So on the next page, if you go on the next page, that's kind of what it says. So you have to derive an expression for the horizontal and vertical forces. So I'll do this for you.
Yeah.
So if we resolve forces vertically, so this force has to be equal to this force, doesn't it?
Yeah.
So t cos theta is going to have to equal mg. What about horizontally?
That's going to be. Shouldn't it equal to the opposite of FC?
It's going to be the same.
That's what I'm saying.
Yeah. So t sine theta is going to equal to mv squared on r.
If it was the same, wouldn't it go like further out? Because they're both going in one direction.
They both go in one. Well, what it means is that these are actually the same force.
Okay.
This one is saying that t cos theta equals mg sine theta, but this is saying that t sine theta is fc.
Okay. Yeah.
So what I want you to do for part B, I want you to, well, it says there, create an expression for v in terms of tan theta, g, and r. Good luck. Oh, and by the way, so you're in 4 unit, yeah?
Yeah.
This is mechanics in 4 unit.
Okay.
If you do this, you'll kill mechanics. What did you get, Brad?
V is greater than or equal to 6.86.
Yeah.
Places.
So that's the minimum speed. So if an object was going at 6.5 per se, it wouldn't actually make the loop.
Mm-hmm.
Doesn't matter what speed it is because doesn't matter what mass it is because the m's cancel.
Yeah. Okay.
Yeah. So the minimum speed is going to be that.
Okay. Sweet. Is this it for circular motion? Oh no, what's this torque?
Oh, right at the end, yeah. So we're almost at the end. Like we will finish circular motion today.
Yeah. Okay. And then what's left to do in this module, the gravitational stuff, something.
Yeah, there's one more inquiry question, then we're done.
Yeah. Okay. Sweet.
Yeah.
Sweet.
I do want you to do question 5 though. Question 5 is a really good question.
Question 5. Okay, I'll give it a shot.
This is a past HSC question.
Yeah. Okay. The James is riding the American Eagle. That one.
Oh no, the Hot Wheels track. So the next one, question 6.
Oh, question 6. Okay.
Yeah.
Said RV, what was that one? Said, you want to do an RV?
Oh no. This was question 2.
Oh.
You have to do question 2 here. Yeah. Oh, you could have just drawn arrow, but it's your booklet, I guess. Yeah. So the question says you want V in terms of tan theta, which is your hint,
Yeah.
G and R. Have you drawn your diagram yet, Radovan?
I'm just drawing it now.
All right, I'll draw mine. So, which is because I don't want you to draw the wrong diagram and everything else is wrong.
Yeah. That's the whole question. Hold on, is this the total height of the Hot Wheels track? The 0.93?
Yes.
Okay. Then how's the radius 0.22?
The radius of the loop.
The radius of the loop.
So that means that the total. That means that the height at the top of the loop is 0.44.
Yeah, that's what I was thinking. Then, like, how does it say the height is 0.93?
Oh, you know, because it's like launched from a ramp.
Oh.
They follow the ramp down.
Oh, okay, I see.
Yeah. So this was my diagram. I hope we had the same diagram.
Yeah, now that I know that it's launched from a ramp, yeah, it'd be like that.
Yeah.
Calculate the energy before these rows. Okay.
There you go.
I'm not trying to figure out the actual motion.
You have this to here. You have to combine those equations somehow to get tan theta as your big hint. What is tan theta equal to?
Cosine sine. Sine equals.
Yeah.
Sine equals 0.
So do something.
Take gravity as negative here.
Just put gravity as do positive, sorry.
Positive.
Well, let me put it, let's look at this. Calculate the energy. Has energy ever been positive? Has energy ever been negative?
No.
Exactly.
Yeah,
We can't have negative energy.
Okay. Hold on, but then if I don't take it as negative, I get minus 1.18.
Did you do minus 0.93?
No, minus 0.93. Oops.
Why'd you do minus 0.93? That's initially how high it is at that point.
Yeah, I see what because I thought it was a change in height once it drops. My bad. But initially, yeah. Calculate the velocity at the bottom of the loop. Okay.
And I'll give you a hint for this one. At B, so in question B, when before the car's released, its kinetic energy is 0. So that means that its potential energy is equal to the mechanical energy.
Yeah.
Figure out what happens at the bottom of the loop.
Yeah.
Yeah, so it's make ground current for velocity.
Equals 4.28.
Yep.
Yep.
Yeah, what we did was, well, the potential energy is going to be 0 at that point. So the kinetic energy is equal to that 1.17.
Yeah, it bottoms out. Yeah. I had a question similar to this in my prelims.
Okay.
Yeah. Did I end up sending you my prelim paper?
No, you didn't.
You want me to send it to you?
Yes, please. I would appreciate that.
Yeah, no, I'll send it to you.
Yes, just send me everything at the end of the lesson, including your answers to the test.
Yeah, no worries. I'll send it all out. Okay. What is the magnitude of the normal force at the bottom of the loop? Okay, so that's mv squared on r equals n minus mg.
Oh, did you get it out? Did you get it? Yeah. That is the formula of the the tangential velocity, geotangent.
Yeah.
That's it. Good job. Well, the questions to this are in the upcoming project, but you already did everything on the incline plane, so we can skip that.
Yeah.
Yeah, that's good. I knew that was okay.
I'm going to use nothing.
Yeah. So that gives us some bank tracks. You said that you did a little bit of bank tracks in school, yeah?
Yeah.
Okay. So the way bank tracks work are very similar to the velodrome. So how it actually works is that in the velodrome, the floor is angled or banked at a certain angle. And the reason why it's banked at a certain angle is because if you follow the math and if you travel at a particular speed called the design speed, there's actually no friction acting on you, which is pretty cool. So this is like road engineers use this when you're traveling around corners and stuff like that. So like, you know, when it's to slow down 35 k's, that's because they're using this. So how it works is, well, let's derive the formula together. This is my object. The object's going to be traveling out like this, like a velodrome. Well, okay. Remember, so you have to differ your thinking slightly because in an inclined plane question, we've been dealing with forces parallel to the slope and perpendicular to the slope. Now, we only want forces vertically or horizontally. And the reason why is because the centripetal force is always going to act horizontally towards the center. So, with that said, instead of mg cos theta, we're going to do just mg.
Yeah.
But, well, we also have normal force, don't we? And we're going to break up the normal force into its components.
Yeah.
So this is going to be m cos theta and sine theta. So I think it's on the next part there actually, at the bottom of the page. All we're going to do is break up these forces. We're going to do the exact same thing. Equate vertically, equate horizontally, and rearrange for V. You okay with that?
Yeah.
Alright, no problem. Best of luck. What did you get for part D?
Part D, normal force equals 12.01.
Yeah, good.
And also,
part
quick
E?
question. I'm on E. Do I take gravity as negative?
Well, you already accounted for the negative because, well, remember the centripetal force acts downwards and so does gravity.
Yeah.
So you don't need to worry about it.
Okay.
Yeah, so you only I never actually take gravity as negative anymore in anything unless I'm doing up and down.
Yeah, okay.
So like even in my projectile motion solutions that you've probably seen for this week's test, when I rearrange, so like in question 1, for example, I put minus half gt squared.
Mm-hmm.
Because for me, g is just 9.8, but you have to attach the direction with it.
Yeah, okay.
So I'm trying to get you to think like that, think intuitively rather than, okay, g equals minus 9.8, sub it in, go from there.
Okay, fair enough. For E, I got 1.47.
Perfect. And that's it.
Yeah. And
This whole question was probably worth about 10 marks.
Yeah. What band would you say? Like, what level was this? 4 maybe?
Oh, each part, A was probably just nothing, who cares?
Yeah.
B, probably band 3, 4, C, band 3, 4, D, band 5, and then E, probably band 6.
Yeah. All right, sweet.
Yeah.
Sweet.
And that brings us to the last thing in this module. We have torque.
Mhm.
So what is torque? Well, torque is a turning force. And so it's not force in the sake of like, okay, I'm applying 5 newtons to turn this force. It's the actual turning force itself. And the formula for torque is given as RF sine theta, where theta is going to be the angle between R, so like the actual thing that you're pushing, and F.
Yep.
Does that make sense?
Mm-hmm.
Okay, there's also a couple of things that we have to know for torque. So the first one is going to be, well, the maximum torque is obviously going to occur when theta is going to equal 90, because sine of 90 equals 1.
Yep.
Another thing is that a clockwise rotation is considered positive torque, and an anti-clockwise rotation is considered negative torque.
Mm-hmm.
Okay. Also, no net torque is adding. So we can also add torques. So if we have a net torque, well, then that means that there's a net turning force.
Mm-hmm.
But if we have no net torque, that means that the object is in uniform circular motion. And the logic behind this is because if we have a torque, we actually have a change in angular velocity.
If there's a change in torque, there's a change in angular velocity.
Yeah,
Okay.
and if there's a change in angular velocity, that means that the speed isn't constant.
Yeah.
And that, congratulations, you just finished the second inquiry question.
Woohoo.
Do the concept check.
Yeah. All right.
Do as many questions as you can. We only have like 10 minutes left. Oh, 15 minutes.
15. Okay.
Never. Congratulations. Good work. What question are you up to, Rad?
Right now on question 3.
Okay, how are you finding talk?
Talk like, look, it's all right, like applying the formula, whatever. But on question 3, it's taking a bit more time.
Okay, no problem. Do you just want to go through the first ones first? So, like for question 1, what'd you get?
8.94.
A big pardon?
8.94 newtons. Is it just RF sine theta? Yeah.
What's your question 1? We may have different question 1s.
The length of a bicycle pedal.
Yeah, I have a different question 1. Okay.
Oh, okay.
Um.
Hold on,
So,
let me open my laptop for a second. It's gonna run out of battery. All right. Question 2, is it a 25 Newton force is applied to a bar? Is that your question 2?
yeah.
Yeah, for that I got 6.93.
Yeah, that's what I got.
All right, sweet.
I swapped question 1 and question 2 around because, well, there's a difficulty jump when it comes to your question 1. So it's been established that the angle is between R and F. Yeah.
For which question?
Oh, back on the previous page where the information is.
Oh yeah, yeah.
But in question 1, it says that the angle between the arm and the vertical.
Oh, it says go minus 90 minus 32.
Yeah.
Stuff. Yeah.
Yeah. So do you see why I switched those questions around?
Yeah, I see.
So you need to be very wary. If they say horizontal, by all means. If they don't say any horizontal or vertical, by all means. If they say vertical, alarm bell should ring 90 minus the angle.
Yeah. Yeah, I didn't read it properly. Okay, is it 14.31?
Yes.
All right, sweet.
And question 3 is a force F is applied to a door hinge.
Yeah, that's the one.
All right, cool. Let's see.
For that, I just got T equals 3 RF on 4.
Yeah. But okay, yeah, I kind of see why you're struggling.
Yeah.
Let me kind of make some progress on this. All right, so I'll assist you for this question. So we know that RF, because it says perpendicular, so that's sine 90, which is 1.
Yeah, hold on. My screen's black.
All right, I'll do it again. Can you see?
Now I can see it. Yeah.
Okay. Because it's perpendicular, sine 90 is 1. So we know that RF equals 20.
I don't think it says 20
For the
anywhere.
first part, yeah, first sentence.
A force F is applied at the edge. Opposite R is perpendicular to the door to produce a torque T. I don't have that 20 Newton meters.
What do you mean you don't know about the 20 Newton meters?
It's not in the question for me.
Oh, is it?
No. For me, look, it says a force F is applied to the edge opposite the door hinge of a door of R of radius R perpendicular to the door to produce torque T. Suppose now that the force is double.
20.
For 20?
I changed the question because it was all theoretical and it was just confusing.
Yeah, okay. So
20 should help.
20. Yeah, okay. RF equals 20. Yeah. Oh, that's easy. In RF, I just sub that in and I get an answer.
Yeah.
Would that equal 15 then?
Give me a second. So that means that it is 3 on 4. What did you say it was?
I got 15. Could you just go 3 times 20 on 4?
Perfect.
Yeah, beautiful.
Good job.
So, because I'm like, there's no way I could get an actual number because if I don't have that 20, you know?
Yeah, but you would have got 3 on 4 T.
Yeah, I got the way I left the question before 20, I got T equals 3, RF on 4.
Yeah.
Yeah.
Perfect.
Sweet. Oh, question 4 looks fun.
How do you go on with that question? And then you'll scroll over it. Well, the m's cancel.
Yeah.
So if you cross out the m's, your line is the exact same as my line, except this is a minus and this is a plus. So v down minus plus. That's all it is.
Easy to remember.
It actually is pretty easy to remember. So, Rad, for question 4, have you figured out that the gravity is a torque itself?
No, I haven't figured that out. No.
Okay. So we have the torque being pulled by the person, yeah?
Yep.
And we're told that's 30 degrees.
Yep.
Okay. But we're also, we know that turning force is going to be counteracted by the force being pushed down by the mass.
Yep.
So that mass, that mgd, is also going to be a torque.
Oh, so I'm supposed to subtract that from the other one.
Yes.
Oh, okay. Oh, I see. Because okay, I see it now. Because there's that level thing in the middle, and then you have R, and then you have the other one. Okay, sweet. Put T1. And then what would the angle be for D? 30 degrees as well?
No, just assume it's straight down.
Just name it straight down. Okay.
Oh, crap. I want to make an alteration. So earlier I said that clockwise rotation is positive torque. It's actually negative torque.
When it goes clockwise.
Anti-clockwise rotation is positive torque.
Anti-clockwise. Okay.
Yeah.
Because I was looking at the plus sign under here. I'm like, what the hell is that?
Yeah.
Okay. So anti-clockwise, positive, clockwise, negative.
Yep.
All right, sweet.
Are you okay to do the rest of the homework?
Yeah, very good.
I apologize for the less than ideal lesson, but hopefully it kind of worked out.
Oh yeah, it worked out fine. We finished the inquiry question. It's all good.
No problem.
So, what is it? 7 o'clock. Yeah, 7 o'clock. All right. Yeah. We'll see you next week then.
See you next week, Rad. Thanks for coming.
Yeah. Thanks for the lesson, man. See ya.
Bye-bye.